Good morning, good afternoon, Data Fam.
Hello.
How are you? We're ready for the I guess we'll say the first pitch.
Yeah.
Hopefully you can hear me all. You can all hear me.
Nice.
My name is Gordon Allett, and I'm the president and CEO of BroadPeak. And we've got bleachers in the back. It's theoretically sunshine outside, and we're about to talk about baseball. So this session's called Moneyball, and there's a few reasons that we called it this. So obviously we're going to talk about baseball. Even if you don't like baseball, I think that you're going to get something pretty important out of this. And part of the reason that we called it Moneyball, it's really based on a book and a movie, which of course starred Brad Pitt. So if you haven't seen that movie, I'm not going to give away any spoilers. But this is a very important story. And I think it captures the spirit of what we're all doing here, which is it really all comes down to this: fact-based decision making. So in baseball, for a very long time, there's a history of judging players by non-fact-based criteria: what the player looked like, how the player threw the baseball, just really very highly subjective factors. And it was Billy Beane who kind of broke through as a manager and said, listen, we're going to use data-based analysis in order to form a team. So with that, we have our very own Brad Pitt, who's going to be walking you through what we've done. So in a nutshell, we're going to be walking through the 2019 baseball season, where we have ingested into K3 the entire play-by-play of every single play in the 2019 season, and what happened, and how it's visualized in Tableau, which Scott is going to take us all through. So I'll turn it over to you,
Scott Nicholson, big baseball fan. Hopefully there's a lot of other big baseball fans out here as well. Okay, so right off the bat, what we're looking at here is a dashboard that's going to give you some insight into events that occur on the offensive side of the game. So just walking through one by one what these visualizations are representing. The first one has been really critical in actually dictating batter strategy and their approach to batting right now. We're visualizing launch angle and launch speed, and what we're referring to is the ball coming off the bat when it's actually contact is made. So on the y-axis, intuitively, we have launch angle. If you're up in this range, you've gotten under the ball and you're hitting a pop-up. If you're down in this range, you've driven the ball into the ground. And along the x-axis, you're looking at launch speed or exit velocity, depending on who you're referring to. On the right-hand side, these are harder hit balls. Off to the left-hand side, these are softer hit balls. The right-hand side is a pretty familiar image to casual fans, expert fans. It's a baseball diamond. This is where batted balls landed on the field. The color coding you're looking at in terms of these two graphics represents the type of event that occurred in relation to the batted ball. And down in the bottom left, you're looking at pitch locations. The color coding here, orange is a ball, red is a strike, be it a called strike, swing and miss, foul tip, what have you. And the bottom right is actually looking at one of the important value representations of a player in today's game, something general managers are interested in, something even casual fans are starting to get interested in, which is wins above replacement. So we actually are looking at two data sets here fundamentally. The first three graphics that I referred to come from a baseball API that's offered by MLB. We normalize that data, and we're actually able to join it to data from baseballreference.com that offers the WAR statistics day over day, so that we can actually then go back and look at what your incremental WAR was for a single game. WAR is often talked about in terms of a player's value over the course of the season, but it's really just an aggregation of individual events. And specifically when you look at offensive WAR, it's run values associated with a player's at-bats and plate appearances that ultimately result in a WAR statistic. So this is per player per game down in the right-hand corner. Where this gets a little bit interesting is when we go back to the idea of strategy for a batter. Batters are very concerned right now with their swing trajectory and how that affects launch angle, because if you're a casual fan, you may have noticed baseball is moving towards binary events, strikeouts and home runs. Guys want to hit the ball hard, they want to get it at the right angle. And that's for a very clear reason. When we go ahead and filter this, these are all the home runs. You see, it's very tightly clustered here because they know if they hit it on the right spot and they get good contact, they get under the ball a bit but not too much, it's going to result in a home run pretty consistently.
It's a very good example of baseball, of like actual players who are now changing their actual athletic strategy based on data.
Yep.
So that it's the data that's driving this into the binary events.
Exactly. And they're responding to what their coaches and general managers are seeing. And it's, pretty consistent out here. This is a generic baseball diamond, and of course every baseball diamond's a little bit different. So you can understand why certain events might not be home runs when they're out here, but at Fenway Park they probably are. But there's some interesting outliers here, like this is sort of interesting, and I want to take a look at what this is like. We were just looking at this earlier today, so we brought GIFs in here so that we can actually take a look and explain these sort of anomalies, and you might wonder what's going on, and you're about to see. Ooh. So it's actually an inside the park home run. I feel bad for these guys, but that's how you can sort of use this to get into the actual specific events that, result in these patterns, and the outliers, of course, are interesting. But beyond just home runs, we can take a look at singles because those are also pretty interesting. So if I go ahead and filter by singles, you get a very different type of a pattern over here. I'm just going to back out my filters. Here. You get a very different sort of a pattern coming through.
There we go.
So if you take a look at the left-hand side, weaker hit singles are all on the upward trajectory portion of the graphic. And that's because if you hit a ball softly, you got to get it over the infielders. Infielders can cover a lot of ground these days, especially with the shift. But if you can bloop it over the infielder's head and drop it in underneath the outfielders, you're likely to end up with a single. Now on the right-hand side, if you got a hard hit ball, you're probably lining that and you're not getting a whole lot of lift on the ball. If you were lifting a little further and you're really hitting it hard out here in the 110 mile an hour range, you're probably gonna end up with a home run like we just saw with the cluster that we looked at earlier. Let's go ahead and take a look at one example of a single that managed to sneak in over the infield. Right there. He just finds the sweet spot. He finds the weak spot in the defense right there. Now we want to take a look at one example of a single batter's performance that was pretty impressive. I'm a Brewers fan, so I actually want to go ahead and take a look at what Christian Yelich did on April 15th. Just gonna back up my filters again. And let me just move on to what we can sort of do with data transformation. So what we're looking at here is data as it came on directly from the baseball API, the MLB API. So this is sort of another view of the spray chart that we were just taking a look at. It's more or less familiar. It looks roughly like a diamond, but we're looking at it from a perspective that as fans we're not used to. You're looking at it from the center fielder's perspective or for somebody who's out in the bleachers. And it's, it's somewhat interesting, but it's also not intuitive to somebody who's looking at a single data point. It's all centered around a sort of arbitrary value 130 here on the x-axis. So if you're looking at a single hit and you're in the database, you have no sense of where exactly that went. So we want to be able to do some transformations that makes the data a little more intuitive to understand. and shapes it for us to have a recognizable view. So you transform the data and you get a much more recognizable shape. You also reveal some interesting patterns. If you take a look at this sort of three-toed sloth look here, what you're looking at is this lighter green in the gaps, those are doubles. This turquoise color located around the outfielders, these are outs. Sort of makes sense. MLB outfielders can cover a lot of ground. And if you're hitting the ball in that direction, you're probably gonna end up with a fly ball that gets caught by the outfielder. If you find the gaps, you end up with a double pretty frequently. And now I've got all my data located around a normal value. We've normalized it, it's centered around 0, so it's easy to understand that anything hit to the negative side on the x-axis is heading towards left field, positive side towards right field. It's just intuitive for us. It's a similar story with the ball and strike locations we looked at before. MLB provides us with some indication of zone, which may or may not be interesting. You can see there are multiple zones that are color-coded here that are outside of the strike zone, and then 9 zones that are within the strike zone. That may be super useful for you if you want to do some really granular analysis of, let's say, a pitcher's approach on a certain count. But if you just want to filter your data and facet it around balls and strikes, you want to actually have the more meaningful data, and you want to transform it in a way that makes it easier for you to get to the analysis that you want.
So if you mentally bookmark that, we're going to come back to that of how we actually made these transformations in K3 to shape the data.
Exactly. But the offense gets a lot of love, but defensive statistics are just as important. So one of the advanced statistics that MLB offers is this concept of a weighted on-base average. So they take a look at the launch speed and launch angle coming off the bat, what we were looking at earlier, and you can actually assess the probability that just based on those two data points alone, something will be a single, double, triple, or a home run. Then you take it a step further. Over the course of a season, all those events, singles, doubles, triples, and home runs, have expected run values associated with them. So when you put those probabilities together with their likely values, what you get is an approximation or an estimation of the run value of a hit before you know what event has occurred. Now, of course, all those events actually are realized, and you may surpass your expected run value, you may underachieve. What we did is some work to identify who a ball was hit to, what defender the ball was hit to, and take a look at which defenders were most effective at reducing realized run value over time. Now, there's a lot of pink on the screen and a few other colors. Those are center fielders. Now, balls hit to center field are usually hit on the nose. They've got a lot of velocity to them, and they're more likely to be a home run than they are if they're hit towards the shortstop. That sort of makes sense. So they've got a lot more capacity to save runs as opposed to other position players in the field. One of the reasons I wanted to put this together is, I love watching web gems. I want to find really cool defensive plays. And I like watching Billy Hamilton. He's an incredible athlete, really outstanding center fielder. So I filtered this down and I take a look at the events where he actually realized some savings on expected run value of a play. And I get some interesting data points here. Some he's turning a double into a single, a likely double I should say, into a single, or what have you. But there's an interesting field out here right at the outfield wall that I'd like to take a look at as well, because how on earth did he get to this ball?
Got it.
Because he has no regard for his health. and he's an outstanding athlete with great focus. So this is all great, but of course we want to know how we arrive at this data and what we do to stitch it together, and Gordon's going to talk us through that.
Thanks, Scott. So Basically, so our application K3 is how we brought all this data together and harmonized it. So it's multiple data sets. So how we got a GIF onto every single play and aligned that and stitched that together. So this is the extreme data portion of the program. So the primary vehicle is the connection to MLB. So MLB does, they do expose a REST API on a play-by-play basis. So, and it's not real time, but it's also not end of day. I mean, it is kind of feeding data throughout the course of the day. And this is a lot. It is a very, very rich data set, as you can see. I mean, it has absolutely every single event, what happened, who was on first, second, third, where the ball was hit on the field, every single data point. And so philosophically, and I hate to take a detour, but this is, our philosophy in terms of how we manage the data is to save everything. So the thing we're doing in K3 in order to harmonize it is, so we have the first tab, which is source. So this is the data as received from whatever data source it happens to be in exactly the raw format, right? So philosophically, there's a reason for that, is because we as data analysts, it is a certainty that we will have to go back to the raw data at some point in time. So I'm going to do all kinds of transformations and cleanups and validations in K3, but at the end of the day, I always need the ability to go back to the raw data set. Now, many of you out here probably work for large corporations, and we've experienced the challenge, which is many of you have fought hard battles to get the raw data in your organization. So sometimes it's not that easy to get, but once you get it, we save it. And then the target side, this is the ETL portion. So this is the transformed portion of the data set. And there's a number of reasons that we'll do that. So like the first ETL function might be something like Scott talked about before. So if I go to a mapping called ball strike, so this is often called a crosswalk or a mapping, but what I'm saying is, so coming from the MLB, they think about the batter strike box as a zone, and these are the zones that Scott was just talking about. And for us, that's fine on the raw data side, but on the other side, I want to make sure that I have it in my format. So for us, we're actually just going to break this down into strikes and balls. So when it's visualized in Tableau, it's in my format, but I always have access to the raw. So the way K3 does this is we're feeding data, and it's a real-time transformation. So the second that it sees a zone of 5, it's going to automatically call that a ball/strike of strike. And that's how the data is populated. There's another sort of, as you can imagine, there's a lot of connections between different systems and connecting data pieces to data pieces. There's another very important ETL aspect, which we created a rules engine. It's a data rules engine. And what it allows you to do is to create case statements for your data. So what's a case statement? It's a when, then, and else statement. So I can say things like, for example, probable home run. So when the launch angle is greater than 27 degrees or less than 42 degrees, and the ball speed is over 100 miles an hour, Nate Silver says that's a statistical home run. So you have hit the ball in a fashion that it is almost certainty that, statistically speaking, you have hit a home run. So it's just a little piece of metadata that can go along with the data set. But this is how we end up creating additional data dimensions that Scott can walk you through. What was the one that you were going to talk about? I forgot.
Oh, up at the top. Take a look at that spray chart transformation as an example. So we want to do some sort of a transformation on these initial values HCX and HCY that don't have intuitive meaning if you're just looking at an isolated data point. And we want to, appropriate the transformation or approximate the transformation that's going to represent a baseball diamond. Of course, we have to check for non-nullness before we do that. Otherwise, you might end up with errors coming through, and you want to make sure that you're doing safe operations. So here, we can use any valid Java expression in a formula rule to modify those values. And if we find later on that the data is changing downstream, we can go back in, modify this rule, and have it apply to new records or re-push the records we've already seen to transform them again.
So the rules engine allows us to do a lot of the grunt work that I'm sure a lot of you face. So, it's the typical, look, there's a date time coming in, and it's in an Oracle date time format, and I just need a date, right? So, and I have a SQL Server date time format, and I need to line it up. So these are the kind of things where it's very easy to just throw a formula. And the big idea is that we want to make K3 operable by somebody that is not super code proficient, right? So it's a low code environment. A lot of it is because it helps the sustainability of the ETL. So if I go out and I write a big script in Python to do some sort of transformation, that's great, I get it done, but I am now the proud owner of that code forever. And so anybody who wants to make a change has to come back through me, and it creates a real organizational bottleneck. So the whole idea is to get that out of there. What was next?
A great example of what you were just referring to. The way we join the two data sets, as I alluded to before, uses these sort of date formulas. So we had files that had dates labeled on them coming from the baseball reference side, and we had game dates that were natively contained in the records on the MLB API side. So we need to use the file names to actually pull in the dates so that we can actually perform the join. So this is how we're doing the harmonization across data sets. So for instance, we can actually natively extract file names through K3. We can use Java formulas to select a substring of that, and then we can actually form a new date using the Java date utils package, and then that becomes our join factor in the future.
Seeing the inventory of all of the things. So a lot of people talk about, well, listen, I have a lot of fields that I have to manage. There's a lot of data elements that I have to manage. So we just present them here right in the application where you can go directly through. You can see every single field to figure out how it's operating currently in the system. And then also the ability to always go back to the data stream, and if you need to make a change, you can make a change in a mapping or a rule and just rerun it. And so that's, at the end of the day, that's how we bring the data together to create some type of analytic in Tableau and pull together whatever it happens to be so that we can actually see a bit of the data from the noise.
Exactly.
So unfortunately they're not allowing us to do a Q&A, which we were hoping to do, but we do have, it's baseball hat day today at the ballpark, so we have hats for anybody that's interested, and I want to thank you all for your time.
Thank you.